Quantum Mechanics by Maple. Part 14. Mathematical Tools in Quantum Mechanics. Ordinary differential equations and boundary conditions. Quantum Mechanics by Maple is a complete course, contains 38 videos for beginners. During this course, student will be able to use Maple step by step in quantum mechanics. The first 10 videos of Quantum Mechanics by Maple introduce and discuss computations and the types of computations, including symbolic and numeric computations. Moreover, they discuss how to reduce the errors and restricting the domain for performing computations in the real number system. From the 11th video of this series, we will introduce and discuss mathematical tools in quantum mechanics, with performing computations for them. The 11th video of Quantum Mechanics by Maple discusses equations in physics and solving equations. The 12th video of this series discusses inequations in physics and solving inequations. The 13th video of Quantum Mechanics by Maple discusses ordinary differential equations in physics and solving this type of equations. This video is the 14th video of Quantum Mechanics by Maple and discusses ordinary differential equations and boundary value conditions. Moreover, in this video, we are going to solve ordinary differential equations with boundary conditions. In mathematics, in the field of differential equations, a boundary value problem is a set of additional constraints and restrictions, called the boundary conditions. A solution to a boundary value problem is a solution to the differential equation, which also satisfies the boundary conditions. At first, we will try to link differential equations and boundary conditions with our real world and explain why they are important for science and particularly for physics. According to dialectics, in our universe, 1. Nothing is complete and perfect. 2. Nothing is absolute. The terms complete and perfect denote whatever is free from transformation, motion, and change. The term absolute denotes whatever is free from any connection, interaction, condition, limitation, constriction or restriction, and independent from any other element or factor. Now we are going to determine the consequences of these dialectical expressions in science and particularly in physics. 1. According to dialectics, nothing is complete and perfect. This dialectical expression denotes, in the world nothing remains constant. Everything is in a perpetual state of transformation, motion, and change. Motion is the mode of existence of matter. To be means, to be in motion. The world is integrating and disintegrating. It never attains ultimate perfection. As it expressed earlier in 13th video of this series, in order to express the perpetual state of transformation, motion, and change, science uses a special type of equation. This special type of equations that expresses the perpetual state of transformation, motion, and change, in science and particularly in physics, is called differential equations. 2. According to dialectics, nothing is absolute. This dialectical expression denotes In the world nothing stands by itself. Everything in the world is connected with all the other things. There is an infinite web of connections, from the smallest structures, like as neutrinos, to largest structures, such as superclusters of galaxies. An endless chain connects everything with all the other things. This chain of the universe has never been broken. It unites all objects and processes in a single whole. For dialectics, the transformation, motion, and change of a body, without any connection and interaction, doesn't exist. The dialectics does not seek the transformation, motion, and change of a body, without any connection and interaction with other bodies. Therefore, it is contrary to the scientific world view, and even common sense, to speak about the existing of only one body, without any connection with other bodies. This universal connection and interconnection of the elements, within the whole at any level, form an essential condition, constriction and restriction, for the dynamic balance of systems. As an example, in our solar system, gravitational connection and interaction between the Earth and the Sun restricts and constricts the Earth to move around the Sun. So, dialectics enables us to see things not only in perpetual state of transformation, motion and change, but also in their connections and interactions. And these connections and interactions of the elements form essential conditions, constrictions and restrictions for the elements and the systems. Now we are going to link these consequences of dialectical expressions with differential equations and boundary conditions. As differential equations express the perpetual state of transformation, motion, and change in science and particularly in physics. Differential equations with boundary conditions express not only the perpetual state of transformation, motion, and change, but also connections, interactions and essential conditions and restrictions in science and particularly in physics. As an example, in physics and mathematics, in the area of dynamical systems, a double pendulum is a simple physical system that links the dialectical concepts of motion and interaction to differential equations and boundary conditions as follows. 1. The general motion of the double pendulum can be described by a set of coupled ordinary differential equations. 2. The general connections and interactions between each pendulum can be described by a set of boundary conditions. So, in macro part of our universe, in meso part of our universe, and in micro part of our universe. 1. The perpetual state of transformation, motion, and change each element is expressed by differential equations. 2. The connections and interactions each element restrict its motion and change, and are expressed by a set of boundary conditions. 3. The perpetual state of transformation, motion, change and connections and interactions each element are expressed by differential equations with boundary conditions. So, differential equations with boundary conditions express not only perpetual state of transformation, motion and change, but also connections and interactions. The universal connections and interactions among systems constrain and restrict some parameters and variables in the connected systems. Briefly. 1. Differential equations express the perpetual state of transformation, motion, and change in science, and particularly in physics. 2. Differential equations with boundary conditions express not only perpetual state of transformation, motion and change, but also connections and interactions. That is why differential equations with boundary conditions, in science and particularly in physics, are so important. As it expressed earlier in 13th video of this series, Maple can solve ordinary differential equations and ordinary differential equation systems, including initial value and boundary value problems, symbolically and numerically. In order to perform computation and solve ordinary differential equations with boundary conditions by Maple, we can use the following methods. 1. Using ODE analyzer. 2. Using dsolve command. 3. Using context menus. In the previous video, we applied all these three methods for solving ordinary differential equations. In this video, for more simplicity and brevity, we will apply the first method and use ODE analyzer. We will use ODE analyzer for solving ordinary differential equations with boundary conditions, symbolically and numerically. In order to solve ordinary differential equations with boundary conditions, symbolically and numerically, by using ODE analyzer, we are going to solve the following example. Now we use ODE analyzer for solving this ordinary differential equation with boundary conditions. As it expressed earlier, the ODE analyzer assistant is a point-and-click interface to the Maple ODE solving routines. To open the ODE analyzer, from the Tools menu, select Assistants. And then, select ODE Analyzer. The ODE Analyzer Assistant is displayed. In the main ODE Analyzer Assistant window, you can define ordinary differential equations, initial or boundary value conditions, and parameters. After defining an ordinary differential equation, you can solve it numerically or symbolically. At first, let's solve the ordinary differential equations with boundary conditions symbolically. So, Maple solves the ordinary differential equations with boundary conditions symbolically. As well, its plot is as it expressed earlier in the 6th video. If Maple by symbolic or exact computation does not find any solutions, it is recommended that you use numeric or floating point computation. Now, let's solve the ordinary differential equations with boundary conditions numerically. Maple solves the ordinary differential equations with boundary conditions numerically and finds the function value at each point. As we know, according to the boundary conditions for this example, at t equals 0, the function value v and its derivation v prime, respectively, are 5 and 3. Now, let's find the function values at the following points. If t equals 0.5, then the function value v and its derivation v prime are If t equals 1, then the function value v and its derivation v prime are If t equals 3, then the function value v and its derivation v prime are If t equals 8, then the function value v and its derivation v prime are If t equals 11, then the function value v and its derivation v prime are If t equals 17, then the function value v and its derivation v prime are If t equals 38, then the function value v and its derivation v prime are As well, its plot shows the function values v at each point of t. In the next video, we will discuss partial differential equations by Maple.